afternoon. I am Tommaso Guffanti. I am a postdoctoral scholar in the Stanford Space Rendezvous Lab. And here at SLAB, we're responsible for developing the guidance, navigation, and control flight software of the VISORS mission. You already know the context of this mission. So we are going to go mainly through the requirements that drive the design of the guidance, navigation, and control subsystem, and then detail the main features of the GNC subsystem architecture, input-output algorithms, fault detection, identification, and recovery, the strategy, models, and uncertain sources, and then diving into the flight software testing, mainly integrated software testing with then overview of the planned hardware-in-the-loop testing schedule. So there are two main high-level requirements that drive the design of the guidance, navigation, and control subsystem. One are the scientific requirements. In particular, we want to keep the relative. So this is obviously a telescopic mission. So we aim to align at 40-meter separation with sub-centimeter accuracy a spacecraft which contains a detector and a spacecraft which contains an optic. In particular, the sunlight has to pass through the optic to reaching then the detector. And in order to fulfill the scientific requirements, which are on image focus, pointing accuracy, and image drift, substantially we need to keep these two CubeSats aligned with tolerances which are of 18 millimeters and 15 millimeters in the lateral and longitudinal direction on the line of sight, and with a lateral velocity during observation of 10 seconds duration of 0.2 millimeter seconds. These are incredibly tight control requirements, therefore we don't foresee achieving them deterministically all the time, but instead we have a requirement which is a likelihood of success of 20% of the total attempted observation. This is the scientific requirement. The other requirement instead, as you can clearly imagine, is a safety requirement, since we are flying at such close separation, 40-meter separation. We have formation flying at 40-meter separation in orbit. We need to guarantee that the formation is collision safe, both in nominal operations, but also in case of contingencies that may affect substantially any subsystem of the CubeSats. And in order to be fault tolerant safe, we have been designing this, substantially the formation flying concept and the GNC architecture to be both passively safe, but also rely on reactive collision avoidance when needed. So substantially the GNC flight software will lives on the OS software app on the bus onboard computer. And in particular, living in the host software app, it will interface itself with many other relevant subsystems on the CubeSats. Here we are listing substantially all the relevant ones, all of them. In particular, the ADCS subsystem. In particular, we will receive attitude information through time and tone from the spacecraft bus, which is designed by Blue Canyon Technology. Then we receive raw GPS measurements from the GPS receivers. The two CubeSats will exchange relevant information through inter-satellite link, which lives instead on the payload bus. Moreover, we obviously will command maneuvers to the propulsion system, which is commercial off the shelf, designed by Georgia Tech, and it lives also on the payload bus. Moreover, GNC has its own guidance, navigation, and control fault detection, identification, and recovery module, but this module does interface with the overall FDIR of the CubeSat, which is designed also by Georgia Tech and lives on the OS software, is implemented on the OS software app. Finally, obviously, the GNC subsystem will obviously interface directly with the ground through ground communication, uplink and downlink. Looking inside at the green box, specifically, obviously, the gas navigation control subsystem is characterized by data interface and shared functionality models, which interface itself with the exterior, with HSA, but then it is characterized by a navigation block, a maneuver planning block, a collision detection block, which are independent and communicate with each other, and also a GNC FDIR block. Going briefly through the input and outputs, here we present essentially an overview of the input and output characterized by receiving a subsystem, and instead we are characterizing more like the specific output which are ejected by GNC. Here I don't want to go too much into the details, but for giving like a high level idea, for example, we will receive GNSS GPS measurements every 10 seconds. So we'll have available a new estimate of our state every 10 seconds. Then this state estimate is going to be actually downsampled by the maneuver planning logic, which instead is going to usually plan maneuver at slightly less frequent pace. In particular, maneuver is going to be planned in any in an interval which ran from 45 seconds during scientific operations, very close to scientific observations, to 0.5 orbits during, for example, transfer operations. And obviously we have a variety of outputs, which probably I'm going to touch base then further in the next slides. So for giving an overview of the algorithms, so this is a very sophisticated mission. For achieving this kind of high-level scientific requirements, we need to rely on substantially algorithms we've never viewed before on spacecraft. And this more or less throughout the full guidance, navigation, control, and safety pipeline. Starting from navigation uses differential GPS. Differential GPS with integer ambiguity resolution, and we have specifically the capability of turning integer ambiguity resolution on and off. So disambiguating on the uncertainty on the wavelength counts of the differential carrier phase measurement, and you can clearly see that differential GPS with integer ambiguity resolution on aims to provide us a sub-centimeter relative position accurate solution and a 50 micrometer seconds relative velocity solution, which should be enough for fulfilling the scientific requirements. Whereas when integer ambiguity resolution is off, obviously we won't be capable of formation flying and aligning at such high accuracy, but instead we will still be capable of, for example, station keeping during standby mode when we're gonna really focus on, for example, downlink and other operational needs. From an impulsive control standpoint, we have a suite of impulsive control algorithms which essentially range from analytical, fuel optimal impulsive solution with partial flight heritage. For example, for reconfiguration, these are trim B in normal plane or trim impulsive in tangential plane solution with maneuver frequency every half an orbit with accuracy substantially on the order of 1 to 10 meters. We also have novel analytical escape solution, which will be substantially computed when we need to escape as soon as possible, and they are going to provide a delta V. Usually can be generated in the RTN, in generic RTN direction. Then during scientific operation, when we need to substantially reduce our control accuracy down to the substantially centimeter level, instead we will rely on optimization-based control algorithms, which has also been are novel, which have been also designed at SLAB, but which substantially the underlying optimization, convex optimization problem solved ranges from second-order cone program to quadratic program, and even to some kind of smart and very simple least square based optimal control solutions. From a safety standpoint, as I mentioned before, we will rely both on passive and reactive safety. Passive safety means that the spacecraft are guaranteed to be safe even in the case of sudden control loss of any of the of any of the two spacecraft, and in particular of the spacecraft which is like instantaneously maneuvering. And in particular, the safe separation on the generating uncontrolled trajectory is guaranteed to be collision safe for at least to orbit in the RN plane of at least 5 meters. From a reactive standpoint, we're gonna check for passive safety in the collision detection block substantially every time we have a new state estimate, so as frequent as every 10 seconds. And if the passive safety margin is found to be violated, given the most updated state estimate, we will plan a reaction maneuver using the analytical escape logic. From fault detection, identification, and recovery, as I mentioned before, we need to interface with HSA FDIR. And this happen on multiple levels, let's put it this way. In particular, like the GNC will communicate to HSA FDIR if either nav or control are incapable or they are subject to some kind of malfunctioning. And this GNC incapability flag usually is expected to trigger from HSA a roll switch flag, so a roll switch flag. So if, for example, the maneuver planning doesn't work on the active spacecraft, we are going to throw a GNC incapability flag, and HSA FDIR is going to command a roll switch, so the other spacecraft is going to become active. But if at any time the collision detection block, for example, detects a passive safety violation, we will communicate this passive safety violation to HSA FDIR, which substantially will handshake and answer us with an escape flag, which triggers to the maneuver planner, which substantially asks the maneuver planner this escape maneuver as soon as possible. Furthermore, when like a non-GNC fault happen, so like in the very bottom layer, when substantially a fault which is not GNC related, but is like related to any other subsystem happen, there are two possible reactions. Either we mitigate substantially this fault by switching role, or we mitigate, for example, if we are in science, we may mitigate this non-GNC fault by commanding by commanding a transfer back to standby. And if you're actually able to transfer back to standby, good, but if at any time of this transfer back to standby, maybe we detect a passive safety violation, then obviously we're going to trigger an escape. So this is kind of like a very multi-layer and robust architecture. The GNC, as mentioned, the GNC subsystem is going to contain various modules that substantially enables the various functionality needed on board the subsystem. And this model obviously range from dynamics models, spacecraft, features and internal geometry models, actuation behavior, but also obviously we receive as input, like for example, through time at tone, the attitude information, which is affected by uncertainty, as well as obviously like measurement from like the GPS receiver. The key aspect here is that when we have so many models which contain uncertain parameters, it's very important to identify what are like the most uncertain parameters which may substantially affect or disrupt the performance of your architecture. And in particular, we have been highlighting few key uncertain parameters which are planned to kind of like affect the performance of our subsystem. And these are specifically the position of the center of mass, because the knowledge on the position of the center of mass. Because if we know the center of mass of the two spacecraft very inaccurately, since we need to ultimately align the scientific instrument passing through like the center of masses where actually like the dynamic forces act, we're just going to achieve a very bad alignment because we don't actually know where, we know with very low accuracy the vector which connect the center of mass to the position of the scientific instruments. Moreover, the propulsion system is a kind of a commercial propulsion system developed by GT, which is characterized by pretty substantial maneuver execution errors, which here are modeled at the moment as especially Gaussian white noises on the magnitude and on the direction of executed maneuvers. In reality, the actual behavior of the propulsion system is more expected to be kind of like biased plus an aleatory component. So maybe this model can be improved in the future. Nevertheless, stress test our GNC subsystem on this kind of like Gaussian, with you introducing this kind of like Gaussian white noise on such a broad range of 1 sigma values, it kind of like capture all the possible errors, and it's kind of a very good stress test, of which we're going to show the results. So from an integrated software perspective, testing perspective, so we are running both testing just on software, and we plan also to run tests, obviously including hardware. But in either cases, let's put it this way, we need to simulate all the surrounding subsystem and also the dynamics in space that obviously dictate the behavior, the underlying behavior of the GNC, the GNC functioning. And in particular, as you can clearly see here, obviously we are emulating the GNSS constellation. The emulator output is fed ideally to the SLAP GPS receiver, which then provides road GPS measurements to nav. But we have also have an option of doing this kind of simulation fully on software. Then we are simulating kind of like fake time and tone information for having input attitude into the GNC subsystem. On the output side, we are simulating cross-link functionalities, and also we are simulating actuation, as mentioned before. Moreover, we are simulating the interfacing between GNC FDIR and HSA FDIR, which by triggering possible like simulated faults. And obviously we have a ground truth dynamic model. And this kind of like testing pipeline, which I said is valuable both for like just software and integrated hardware testing, enables us to run both like mission mode simulations, so like long time scale simulation, but also like more focused like sensitivity analysis and Monte Carlo testing, for example, just in science mode on the effect on alignment of specific like uncertain parameters. So let's start with some nav performances. I'm super out of time, by the way. I need to like, I don't know, either we remove slides, but in any case, I'm gonna finish the presentation, but then I have to figure it out. Yeah, it is.
Can you ask for 30 minutes?
No, it's like a 15 plus 5. So
it's ridiculous, 15 minutes.
So we need to. I'm already out of time. So either we remove some slides or I don't know. But let me finish this presentation. I'll remove some. So like we were showing here some navigation results. In particular, we are showing on the left. We are showing like the classic like envelopes of like navigation accuracies and correspondence covariance bounds. And the key message here is that we are indeed able of obtaining kind of like the navigation performances we were like aiming to in the table I showed before, which are like sub-centimeter accurate navigation solution in relative position and substantially sub-millimeter second, considerably sub-millimeter second relative velocity navigation solution. We're also showing results in terms of like integer ambiguity resolution, in particular like for the single difference carrier space measurement, we're showing the integer error over the mission timeline. And just to mention, this is like a simulation. We start from standby. I mean, as I said, I don't have time in this presentation of like describing all the various stages of the mission, but in any case, there is a standby mode, transfer mode, science mode, and then transfer. This is like the evolution, the nav behavior throughout the full kind of like transferring, science, transfer back. Then we're also obviously showing other relevant metrics as the dilution of precision, which is low, which is good, as well as the number of commonly observed satellites. These plots show, if I'm correct, these plots show especially the trajectory throughout transfer in, science, and transfer back. substantially directly estimated by the onboard navigation. Then we have been also running, as I mentioned previously, some Monte Carlo alignment results on some few key uncertain parameters. Starting from like these first results shows substantially how the alignment performances are affected by a varying value of center of mass position error. So by varying value of our knowledge of the substantially position of the center of mass. And as you can clearly see, I'm particularly in the three plots on the left, I'm showing the longitudinal relative position error, lateral relative position error, lateral relative velocity error as a function obviously like of the Monte Carlo parameters, and then in the plot on the right I'm showing instead the resulting like substantially observation success percentage. And you can, this is like substantially for each Monte Carlo parameter value, we are running 100 observation, and the whisker plot captures the statistics over these like 100 observations. And ultimately, like for the knowledge in the position of the center of mass, we are seeing like kind of like the expected behavior. So the less precisely, the less accurately we know the position of the center of mass, the worse we perform in terms of like scientific alignment. But the truth is that, like looking particularly on the plot on the right, apparently if we know the center of mass with at least more or less, let's say at sub-centimeter level, like lower than like 1 centimeter, actually the alignment performance is actually substantially good. So like over 60%, which is actually pretty impressive, to be honest. More like kind of curious, let's put it this way, or unexpected. I like the results when we do these Monte Carlo runs in terms of like the actuation, maneuver execution error performances. So here I'm showing the same kind of plots for the maneuver magnitude execution error. So we need to put our brain inside these plots 1 second. So sorry, the maneuver magnitude execution error is considered proportional to the size of the maneuver. So this value on the x-axis are like, so we're telling that substantially the maneuver magnitude execution error is like 5%, 10%, 20%, 30%, or 50% of the executed maneuver. The truth is that we are seeing incredibly good results as a function of this like maneuver execution error. So this kind of like sensitivity to of alignment performance to maneuver execution error is like lower than expected, and I'm listing some possible reasons. So first of all, in science mode, the control loop is closed very frequently. So every 5 minutes in long term and every 45 seconds in short term. So this probably permits substantial. So we are recorrecting our plan very, very frequently. So as soon as we implement a maneuver, which is going to be potentially even substantially wrong, but then after like 5 minutes to 45 seconds after, we are replanning it. So we are correcting very, very fast. The second point is actually a point that came out in a discussion with Prof. D'Amico, is that ultimately like the main driver in the terminal alignment accuracy are the very last few maneuvers. Like let's say 1 to 3 maneuvers, which by the way are the one computed using the least square, like the time-fixed least square solver. So the rationale here is that as long as during long-term control we are able to lead this kind of like final maneuver to have to correct for like a relatively small tracking error. So if you're not like diverging completely in tracking error before, but we are able to arrive quite close to observation with a kind of a small tracking error, what means is that this kind of last 1 to 3 maneuvers have to correct for like kind of a small tracking error. Therefore, they're going to be small maneuvers. Therefore, the associated execution magnitude error is going to be small. Moreover, since we are modeling the execution error as a zero mean Gaussian noise on the true maneuver, on the ideal maneuver, this is kind of, I don't know if this is something I added, but I am asking for feedback. But the truth is that just for the nature of the Gaussian distribution, there is a higher probability to be lucky on like very few maneuvers than on like many maneuvers throughout the mission. So if the very, very last few maneuvers are the one that counts, maybe, as I said, we have like just for the nature of the Gaussian distribution, there's higher probability to be kind of like close to the zero mean for like these like very few terminal maneuvers. So as I said, it's good that you have at the very end like just few small maneuvers which dictate the substantially terminal alignment behavior. And this kind of like, the third point is that this kind of like stress the importance of kind of eliminating from the scene any non-random bias present in the propulsion system. Because like any non-random bias kind of like completely biased off like our capability of performing maneuvers. But if we are able to estimate those, then we just have this kind of like Gaussian aleatory component, which doesn't seem to impact too much. This is kind of like the idea. And this analysis is also replicated for like the direction error, but still like the results are kind of similar. So performance which are incredibly good, like 70%.
Wrap it up.
Yeah. Yes. Yeah, I can wrap it up. Yeah, I went too long. Then we are showing collision detection and escape performances. In particular, on the plot on the left, we are showing that our collision detection block is capable of providing a lower bound on the minimum separation on the uncontrolled trajectory with 99% confidence, which is always below like the actual minimum separation. And during escapes, which is like plot on the right, the red line, we are able to kind of like enforce our end separation after escape, and we're able to enforce a rising along track separation, which is actually very, very good. And this is actually like the behavior we want from collision detection and escape. Finally, from a delta V budget perspective, here the moral of the story is that we're doing very well. The only modes in which substantially we are spending more fuel, we are having a delta V which is higher than the one expected in previous analysis are transfers, whereas in all other mission modes substantially we have a delta V consumption which is lower than the one expected. These are L2 norm values, but even if we are introducing like a root square 3, so like a 70% margin for like L1 norm losses when we have to convert from like L2 to L1 in the thruster frame, we are still fuel positive by meter seconds, which will allow us in any case for doing acquisition, reacquisitions, and extra escapes. And by the way, we don't expect a 70% loss. Actually, we're going to improve in the future this analysis for actually, so mapping through attitude to like thruster frame for actually getting the actual L1 value in the thruster frame. And this slide, which is actually probably for this system integration review the most important, I mean, it comes out at the very end, shows our hardware in loop testing plans, which are gonna happen, I would say mainly at SLAB, in which we plan to do a software and hardware in the loop testing on the flat set to evaluate like the functionality and performance of GNC. And we propose a scheduling on the left, substantially from now until like end of this year, more or less. And then at GT instead, we probably plan to do some processor footprint analysis on the real spacecraft hardware, verify interfaces. We plan to give to GT a consolidated ICD by mid-May, and we will be available for like any other like relevant test on the real spacecraft hardware after spring. I mean, in summer GT has no workforce, so probably in fall. And no navigation. Okay. But in any case, these are the next steps. But in any case, we need. These are the next steps.